Hi everybody. I'd like to go over one example with you on how we find the derivative of a function. So let me put here a graph for you. There it is. Okay, so what we're going to do here is I'll give you a function. Like in this case, we saw this before. It's a simple quadratic function, x squared, okay? And here in black is the graph of that function. And what I would like to do is to find the derivative. Let's say, for example, you've been asked to find the derivative of f of x at x equals to 1. Okay. So there are many ways we can ask that question. Okay. Derivative is the definition, is the name we give to the slope at one point. There is another term that we use also called instantaneous rate of change, and we're going to see why they use that term. But basically, so just to refresh our minds a little bit, basically we want to find the slope of this line. So let's see if I can catch the line here. For example, alright, that looks like the tangent line, okay? It's the slope at one point. Okay, so at that particular point, this x equals to 1 here, we would like to find the slope of that line, okay? And we're going to see later that the slope of that line has a lot of applications for it. We can tell how fast, if the function is a profit function, we can tell how fast the function is growing, how fast the profit is growing. If it's a function that tells you where your car is when you're driving, then the slope means the speed and how you're moving your car, how fast you're going with your car. Okay. Anyway, but the essential idea here is that it's a slope at one point. And I told you before in class that to find the slope of a point is kind of it almost seems impossible, because what we learned before about slope is that you need 2 points. Okay. Well, that's exactly what we're going to do. We're going to first, before we find this slope here, we're going to use a temporary point to help us figure out the slope at that one particular point. So let's say, for example, I start here, okay, and so we pick a temporary point here. So this way you create what we call the name of this line now becomes it's called a secant. Okay, it's called a secant line because it crosses 2 points of the curve. Anyway, you don't have to actually memorize that name, but it's called secant. Anyway, when we have a temporary point, then this point will be over here. Well, usually this point should be kind of close to that one. What we're going to do is to move this point here, this red one, towards the first one. Okay, so we're going to try to push this point towards the first one right there. Okay, so this way we will eventually find a line that will be touching that point here. Okay, let's say if this is a temporary point a little bit away from 1, this would be maybe something like 1 plus, I don't know, 1 plus 0.9, okay? Well, if this is 1 plus 0.9, then this would be f of 1 plus 0.9. Okay, so this is f of 1 equals to 1, because when x equals 1, if I plug 1 in here, I get 1 squared, and 1 squared is 1. Now here, this second point, if I plug that into the function, I get 1 plus 0.9 squared. So you can see now the formula for slope, rise over run. Okay, so basically we take rise over run, which in that case would be what? What is the rise here? The rise is this number minus this number, so I'm gonna write this way, f of 1 plus 0.9. You may ask, Professor, why didn't you write just 1.9? Why did you write 1 plus 0.9? Well, because if I write 1 plus 0.9, then you're gonna see the formula better, right? When I write 1 plus 0.9, it really means that you are a little bit away from 1, right? Here's 1, and then you're moving 0.9 units away from 1. Okay, so this way you're going to see the formula show up later in this example. And this is minus f1, which is this. And then run here will be this distance from here to here. Now you can see why I wrote this way, because the distance from here to here, it's this one minus that. Well, which is simply 0.9, right? Distance from here to here is just 0.9. Okay. Now, if you plug that in the calculator, so let me put the calculator here for you. Okay, let's see here. Let me put the function x squared, okay? Then we can play with it. Go vars, y vars, function. Okay, then 1 plus 0.9, that's 1.9. That's 3.621. So again, let me put that in here. Minus, if I plug 1, it will be 1 squared, that's 1. And this is 0.9. Okay, so subtract 1 and then divide by 0.9. Okay, so this number here is 2.9. So that's the slope. That's the slope of this line here, the secant line. Well, but that's not what I'm interested in. So I need to make this second point closer to 1. Okay, so let's use another point. So I'll use another color here, maybe green. Okay, so let's say now let's use another point. Let's say here. Well, if I'm use a point now, this point is closer. Let's say this would be maybe 1 plus 0.2, maybe. Okay. So the y value then becomes f 1 plus 0.2, or 1.2, right? And now my secant line, try to catch the line here. There we go. So I'm trying to draw that line. Okay, let's see if it will work now. All right, there you go. Okay, so now forget the red point. Let's look at the green point there. So that's a new secant. So this point now is closer to the first one. Okay, let's compute again the rise over run and see what happens, okay? Okay, rise over run. Well, that's f of 1.02 minus f of 1, right? So it's, here's the rise, this one minus this number, divided by run. Run now it's from 1 to 1 plus 0.2. So this distance is simply 0.2. Okay? So let's put the calculator here to work for us. Okay, now it's f of 1 plus 0.2, that's 1.2. So I'll put 1.2 there. Okay, 1.44 minus f of 1, I already know what that is, that's simply 1 divided by 0.2. Okay, so let's see what this is. Divided by 0.2, that's 2.2. Okay, so that's the new slope for this second point. Not for the point, but for that secant line, okay, from here, if I draw the line from here to here. You know, but that's not what we want. We want closer and closer to this first point. So you can see what we're doing here. We're making, if we keep doing this, right, look what is happening to this point. It's getting closer and closer to the first one. So therefore, the second point is a little bit away from the 1, so it will get closer and closer. So this number here, the 0.9, 0.2, then that number is decreasing, so it's going towards 0. Okay, so that's why now we're going to use a number here. So let's get closer. So if I get closer, so that could be, for example, 1 plus 0.1 maybe, or let's put this, let's use a little variable called h, okay? So that h is the 0.9, 0.2, and then 0.1, and then 0.01, okay? Eventually, this h is getting closer and closer to 0. So because of that point there, this would be f of 1 plus h. Okay. So if I do that again, rise over run, then rise would be f of 1 plus h minus f of 1. So that's the rise. That's this number minus this number. So that's the rise here. Okay. And then the run, which is this little bit here, that's simply h. Okay. So now at this point, let me show you two ways you can do this. You can do this algebraically. Okay, so just plug 1 plus h into this function here. Right, plug 1 plus h here, and then you will see a big, 1 plus h squared, and then you can expand that. I think we did that in class. Okay, you look at the notes, we did that in class. But let me show you a second approach, and you can use your calculator to do this for you. So what we can do here, so go to your calculator, put the function here on function number 1, okay, and then use the second function here, the y2. So here's the trick. Use that one to input this formula here for you. Okay. So you can do, let's say, bars function. One plus, but instead of h here, let's go ahead and put just simply x. Okay, we don't have the h variable, just put simply x, and then minus f of 1. Well, let me go back here. I need to put parentheses because it needs to be this whole thing divided by h. y1 1 plus x, and then minus y1, everything divided by h. We don't have h, so let's use x. Okay. All right. So now you can see, you can go back here to the main screen. Okay. Let me show this to you again. The first function, the y1, you put the original function here. Okay, the f of x equals to x squared. The second one, you put this formula here, the rise over run. We don't have h, so let's use x in here. Okay, so that's why you have y1, and then 1 plus x minus y1 of 1. Okay, let's go back here to the main screen. Now I can use my calculator to, instead of choosing the first function, I use the second function, and I can compute different values of rise over run. So I can use, like in this case here, the h was 0.9. In this second case here, h was 0.2, right? For example, if I put 0.9, that's the 2.9. See, that's the value we found here. So, and then if I put 0.2, that's 2.2. See, that's this value here. Let's see what happens if I get closer to 0, right? So remember that we are trying to figure out, so the derivative at x equals 1 is the limit of rise over run. Okay, so it's the limit of this big formula here when h approaches 0. Okay, so you need to make h, in the calculator is simply the x value here, okay? You need to make your h as close as possible to 0. So we have 0.9, 0.2, let's try 0.1. So that's 2.1, okay? Let's get closer to 0. 0.1, 2.01, closer. So you look at the h. H is going to 0. All right, let's try maybe like that. That's pretty much 2. Okay, so we can see that this is 2. Okay, so the slope at x equals 1 is 2. So let's look at the picture here for a moment. Okay, so if I had my line, if I had my secant line over here on the rad one, on the rad point, then the slope of the secant line was 2.9. Okay, so now that I brought, let's see if I can bring this down. There. Right. That's the secant of x at x equals to 1, or the tangent line. That we don't call it secant anymore. There we go. Okay. So we brought this point all the way down here. It gets closer and closer to the first point. Okay, that's the idea graphically. But algebraically, this is what we're doing. Okay, we take rise over run and make that h go towards 0. And we found that that's 2. Okay, so this is the slope at x equals 1. Okay, that's the idea.